Oh, what's worse? I can literally put my mouth. My final project.
Okay. Let me say a couple of words about the next homework set. We're gonna get to some of the stuff very soon. The first thing is, first two problems are sort of, work on classification there, finite generated abelian groups. Find up to isomorphism all abelian groups order 2,250. Now, if I asked you for all groups in this order, you should get the pitchforks and the torches and get very angry, right?
Yeah, I'm like, what?
But abelian, not too bad. We're going to see why that's true. Number two, consider the abelian group G, which is Z60, direct sum Z24, direct sum Z36, direct sum Z100, direct sum Z56, direct sum Z48. So it is the direct product of the cyclic groups of order 60, 24, 36, 156. Okay. Find the invariant factor decomposition of G, and then find the elementary divisor decomposition. I haven't told you what this is, but this will be again part of the fundamental theorem of finite generated abelian groups. For the next problem, we make the following definition. Suppose I walk up to you on the street and give you group G. We define G sup 1 to be the commutator subgroup. Right? You all remember that when we had the subgroup generated by all commutators. Well, so you start with G and you get its commutator subgroup. Well, now you've got a new group, this commutator subgroup. You take its commutator subgroup and its commutator subgroup, and that's what you're building here, right? G1 is the commutator subgroup, G2 is the commutator subgroup of the commutator subgroup, and so forth and so on. We say that G is solvable. And actually, there's a reason this is called this. There's a connection between G being a solvable group and you being able to solve certain polynomials in terms of radicals, as a matter of fact. Like, for example, the quadratic formula. And we might see some connections there later. We say that the group is solvable if doing the sequence of commutator subgroups gets you down to the identity eventually. Prove the following. We're going to talk about solvability later, but this is all you really need for now. Prove that if G is solvable and N is a subgroup, then N is also solvable. This is not too hard. Show that if G is solvable and N is normal and is a normal subgroup, then G mod N is solvable. Show that if N is a normal subgroup, then G is solvable if and only if both N and G mod N are solvable. Notice that one correction was done for you in parts A and B. Right? There's only one. Let me also tell you that the proof of this is in the notes, right? But you shouldn't just copy it because it is a notes proof and details need to be added. But you certainly can use that to help yourself out. Number D, apply this. Show that any group of order 675 is solvable. And E, show that if G is any finite P group, then it is also solvable as well. So, any questions? All right.
Yes, I just learned what solvable means. Oh wait, it already shows there, so
Yeah.
you basically use powers like see those subgroups and stuff to prove it.
Great. Okay. We're working up to the classification of abelians, but there's a couple of loose ends that we need to kind of tie up here with regard to what we were talking about before. We had this last time, and we were in the midst of proving it. So when we began the proof last time, we showed, in fact, that and remember, this depended very heavily on the fact that both K and H are normal subgroups. That's what we're assuming here. Now we define a function I'm going to define a function here, and hopefully it's going to be a homomorphism for us. And a typical element of this looks like little h little k, right? And I need an order pair here.
H comma K.
Right. He remembered he's in a math class, so it should be easy, right?
Yeah, it's super easy, you know.
What's the first thing I gotta worry about? Right out of the gate, there's something I should be worried
First
about.
off, check if it's a homomorphism and it's well defined.
Okay, right. First, we need to make sure that this is a function itself that is well defined. Right, because it occurs to me, there might be a different way to write this, correct? Well, so,
First off, our H and K, what's the intersection between these two groups?
okay. This is really the problem with well-definedness. I might say tomato and you say tomato. There might be two different ways to write this. This would certainly get two different outputs. Let's see what happens. Let's manipulate this a little bit. This means K is equal to H inverse H1, K1. And this means multiplying on the right by K1 inverse. Everybody okay? Just a little manipulation of this. Well, what do I know? This thing is in K, and this is in H. So this animal,
So what's the intersection between H and K?
what is the intersection? It is the identity. So this means so I get so what I've shown is under this situation here, there's only one way to write HK, right? Because if I have HK is H1K1, then these two are the same and these two are the same. So the representation HK is unique. So yeah, it is well defined. Because what we've shown along the way is there is no tomato. If this element here, there's only one way to write it, it's H times K. Everybody okay? So that gets unique out. Okay, step 2, is this a homomorphism? Right? Well, suppose H look at f of HK times H1K1. This is, if I maybe I'll put parentheses. Now, what do I know that's might help me out here?
First off, you need to know that, well, K and H can equal like H1K, H1K equals H1.
Right. What I know is when I see an H and a K next to each other, I can plot them. That's what this says. And here's an H and a K next to each other, so I'll plot. This is because of this thing we established last time. right?
Mhm.
But remember, I can't necessarily flop H and H1, but I can flop H1 and K. So this becomes, by our definition of F, that's the way F works. It takes it to this ordered pair. Right. And I don't know much, but I do know this.
Mhm.
Because that's the way multiplication works in the direct product. And that's up to lead. So it's a homomorphism. F of the product is product of the F's. Okay. Finally, we need this to be bijective. We need this to be one-to-one and on to finish this off. This one's not too bad, I think, because suppose HK is an arbitrary element of HK, then F of HK. There we go. I know from whence that comes. Right. And how about the one-to-one? Suppose HK is in kernel of that. Well, let's see, this means F of HK is equal to NH to K. But this is also equal to H. Therefore, H, and this implies that HK one in HK. Therefore, F is kernel string. So that establishes that HK is isomorphic to this. Let me give you a corollary to this. Oh, any questions first? Yes.
Is that should like if we're just sending back to.
Well, so we're going here, right? This is the coda thing. What does a typical element of this look like? That, right? So given that I need to go here, all I have to do is just mash these two together and that's where it comes out.
I don't understand how does that show, set its, vector?
I'm sorry, this what?
Wonderful.
Well, what we've shown is anything in the kernel is one, right? Certainly one's in the kernel, but we've shown that an arbitrary element of the kernel has to be the identity. And that's an equivalent condition for one-to-one, for a homomorphism. A homomorphism is one-to-one if and only if its kernel is true. That's one from a long time ago. Correlate. So this is just the previous result, one extra added condition. H, K, and G subgroups such that, number one, H and K are both normal in G. Two, their intersection is trivial. And three, this is first two are exactly like the previous result. Three, suppose HK suppose those two subgroups put together make all of G. Anybody got the conclusion here?
He is isomorphic to H, right, or H and K.
That is correct. Because what we had last time is these two conditions gave that HK is isomorphic to H cross K, but now HK is G, so there's nothing really to this. But this is actually important because so here's what I'll just call this kind of a remark. Here, H, K, E subgroups. That's fine. 1, 2, 3, 7, 1, 8. We say G is the internal something correct product. of H. Now, I threw in external. What's all this internal external crap? Well, so external, think of it as somebody comes up to you and gives you a bunch of groups, and you just make the direct product with them. They give you a group G, they give you a group H. You say, hey, I'm going to make G cross H. That's external. Somebody gave you G and H, and you made it. This one they call sometimes internal, and I don't think the distinction is really huge, but this one they call internal because you started with your group G and you found subgroups that satisfy these conditions. It's like, hey, I could realize G as the direct product of those two subgroups. And an easy example, I think, is, and we talked about this last time, where you might have H in a single bar, 3 bar, and K is 0 bar, 2 bar, 4 bar. Now, this by itself is a cyclic group, and that's a very convenient way to think about it. It's generated by one good thread. You can also think of this as isomorphic. This is isomorphic to Z2 because this is isomorphic to Z3. No choice because there's prime elements to the subgroups. This is isomorphic to Z2. And with various applications, sometimes it's more convenient to think of this as cyclic generated by a single element. Sometimes it's easier to think of it this way broken up, depending on what you need for your computation, right? Notice what it means to be the direct, in this case, the direct product. I've written it as sum because it's a finite number of groups and it's abelian. It's the same thing in this example. These two groups, their intersection is the identity. And any element in here is a sum of something from here and something from here. And not only that, it's uniquely done, right? How many sums are there? 3, 6. 0 plus 0, 0. Then you get 2, 4. This gives you 3, 5, and 1. So everything can be written. It's a sum from either from those two groups, and it can be done so uniquely. Just to remind you, you've already had this definition in the homework. I'm going to repeat it for you. Definition 710. Let H and K be groups. And P a homomorphism from K into odd H. We define the semidirect product of K with H. uh, consists that have underlying set and multiplication given. H1, K1 times H2, K2, H1, K1, H2, K1, K2. So this is something that you all did in the homework, where this is a twist. Let me point out something, that the easiest automorphism I can think from K into odd H. In fact, the easiest automorphism, many group two. I'm sorry, any homomorphism from K here. You've always got the trivial homomorphism, right? Where you take everything in K to the identity. So what if phi takes every element of K to the identity automorphism? How does this multiplication work then? That is exactly right, because if phi takes every K and K to the identity automorphism, then no matter what K1 is, this is the identity automorphism, which means that thing is just H2. And so in the case, so this is actually a generalization of the direct product in the following sense. If this homomorphism is trivial in the sense that it takes everything to the identity, then you recover the direct product. However, if this is more exotic, you might get something that's a little bit more interesting. Right, so let me give you this following theory. You might want to look at, I want to skip 7-11 because I just kind of talked about it a little bit, but here. Suppose that G is a group and H and K are subgroups such that number one, suppose that H is normal in G. Two, let me discuss this first. This almost looks like that corollary from the direct product. Can anybody tell me what the difference is with this one right here?
K is not normal in G.
Not necessarily, right? The only one we're guaranteed of normality here is H, right? So I dropped the condition that they're both normal. I only need one of them. This condition's the same, only trivial overlap. And this is the same as the corollary. By the way, does this make sense? You betcha. Because all you need is one of those two subgroups to be normal, and HK is a subgroup, right? In fact, you don't even need H to be normal. You just need it to, you need K to be contained in normal algebra. So, everybody with me? So suppose we've got this. Now I've only got one. I've only got one for sure that's normal. Their overlap is trivial. And the product, which is in fact the group because H is normal, is all G. Then G is isomorphic two. So this is the condition. So I gave you the condition of two groups to be, for a group to be a direct product of two subgroups. These are the conditions for a group to be a semi-direct product. So I'm not going to prove this. In fact, you should probably do it yourself just for fun. But what I am going to do is I'm going to take you through most of the details. So suppose, I'll just sketch. I want us to see when this comes up. So let's see, what's the multiplication? Okay, so one of our conditions is we know that HK is equal to G. So, I mean, I don't know about you guys, in kind of the most puzzle, where am I gonna get this fee? Right? Where's this gonna come from? Out of what magic hat is this gonna come? And how's that, how am I gonna get this fee? Well, I know that HK is a sub, in fact, I know HK is all G here by assumption, right? How do I multiply two? If HK is G, I can write every element of G in this form. And how do I multiply? Well, and see, now I'm freaking annoyed. And the reason I'm annoyed is this does not look like an element of HK. This is a mixed bag, HK, HK. I don't see a single element of H, comes a single element of K. Oh, dear me, what will I do? Okay, H is normal, so how's it gonna help us?
H2,
Not necessarily, because with that direct product, I know what you're thinking, you're close. You need them both to be normal, right? Right. So now I'm a little stuck, right, because. Where do you like? Well, so the idea is use the normality. I mean, you guys, that's the key. I wish I had a K1 right there because I know that H is normal. Right? Oh, but I don't, oh, but make there be a K1 there. I can fix that. Right? This is equal to H1, K1, H2, K1 inverse. But now I got to get rid of that K1 inverse with K1, K2. Notice if I cancel the K1 and the K1 inverse, I've got the same string parts like the last one. And what do I know about this? This is in H, which is normal. Everybody agree with that? And this is how I sort of just, this is why H being normal. So now my new thing is in here. Now, can somebody connect this with what's supposed to happen in the semi-direct product? So in the language of semi-direct product, what I have here is H1 comma K1, H2 comma K2. So think of this in commas here. Notice this is an element of H and this is an element of K. Right? So that matches the tail of this. Right? And what goes here? Well, what goes here, I guess, would be H1 times K1, H2, K1 inverse. What's the homomorphism? So the roll of feed from K into H. Can somebody describe how this works? This corresponds to the inner homomorphism. P sub K. And I'm going to tell you what that is. P sub K of H is K H A inverse, which is exactly what we're doing here. This is, in this language here, this is H1 P K1 acting on H2 K1. Right? Because that's exactly what we've done. Is this is the automorphic image of H2 under that conjugation that interoperates. So this isn't really a proof, but I hope that this you'll kind of see what the connection is now with the homomorphism. But actually here what's happening is you're actually getting that interoperates. That's what you need. Yeah.
But doesn't that mean that restrict our definition for the theorem to just the instead of off age, that it would be to in age?
Well, right. So with this one right here, because it's normal, there are semidirect products that you can construct that are not inner automorphisms. For example, for feed, I'm gonna take 0 bar to the identity automorphism, and I'm gonna take 1 bar for pitchfork X minus X. This semidirect product is isomorphic to D3. Right? But it is a semidirect product of 2 abelian groups. And so what you're really looking for is interautomorphisms of G, right? And the automorphisms of H. So H in this case, I guess, to be played by Z3. There are no non-trivial interautomorphisms. Right. What we did do is we did an automorphism of Z3, which of course can't be inner if it's non-trivial. Right. Because Z3 is abelian. But what this does is in the whole group, this gives you kind of an inner automorphism of all D3. Okay, any other questions? By the way, that was a good question.
It's not just the last part. Maybe someone.
This is a special case of something you probably did more general. Second. Structure of finite and finite universe. Abelian. Okay, so we've got some real nice structure theorems here. I'm gonna build up to this with some interesting lemata that will make this a little bit easier, I think, to digest, and then I'll give you a, we'll not quite get to that by Monday. But let me start out with this. I think this limit is terribly interesting. Let G be an abelian. Abelian will be close to blanket in this particular section, as you help the title. P group of order in power. Where when I say P group, of course, I mean that P is prime. G is safe. If and only if G has a unique subgroup order. Okay, so let me make some observations before we stand feet up. First of all, if you have an abelian P group for P to the n, here I'll assume as the n is greater than 1. If you have an abelian P group for the n, then, well, by Cauchy's theorem, you must have an element of order P in there, right? And that means that you have to have at least one subgroup of order P. This is the interesting part. The group is cyclic if and only if there's one and only one subgroup of order P. So that's an interesting criteria. You've got this group of order P to the 10,000. I don't know if it's cyclic or not. All you have to do is look and say, is there or is there not only one subgroup of order P? That's kind of cool. So, this is the easy question. Here, G is cyclic. It contains a unique subgroup of order D forever. D divided by order. This is true for any cyclic group, whether it's for P or not, right? Since P divides order P, which is P again, G has unique subgroup. So you need almost none of this fancy stuff. All you need to, if G is cyclic, it contains one and only one subgroup of order D for any divisor. So since P divides this, it's got a unique subgroup for P. The interesting part is that only the existence of only one, a unique subgroup, means it's cyclic. Yes.
Does that mean that when G is cyclic, then that means that it has a subgroup of every order that divides it?
Yeah, that's right. That's one, yeah, for any cyclic group, let's say it's order, it has one and only one subgroup for every divisor. Right, this theorem we have a long time ago, I don't know about cyclic groups.
Do you know what section of it or chapter?
Probably, I think there's a chapter called classification of cyclic groups, it'll be in there. Forget that, still prove it. It's actually, it's a good exercise, and it's not terribly hard. The interesting part is the existence of only one P group means that this is cyclic. The other direction. We proceed. Next, this theorem included, the next three theorems will be, induction, which is actually very powerful in this, theater here. So, if n equals 1, and order the D, so just right, that was easy. I felt like I got away with something there. Now assume the conclusion for inductive hypothesis. We assume conclusion for all groups of order e to the k, where for all k between 1 and m, and now suppose that the order of the speed plus 1. Okay. Now, how are we gonna deal with this? So suppose
Why was this in?
so
Why was this in?
it doesn't matter so much. The statement is here, and so what I'm doing is I'm assuming that it's up to n, so there's not confusion with this, right? Because this statement is in terms of n. It doesn't really matter if you're more comfortable. It's
I just thought we were doing induction on it.
okay,
That's why. Sorry.
right. Induction on, maybe I should have written induction on the power of P. How's that?
Okay. Sorry, no, that's really good.
So, suppose the order P is P to the n plus 1, and G has a unique subgroup for
See this.
by the way, just for fun, before I stand feet off, if it's got a unique subgroup of order P, how many elements of order P are there? E minus 1. There you go.
Minus 1.
Yeah. Because one of them's the identical, right? Now consider P and G given by P of X is X to the power. P is a homomorphism. Notice that the input is in G, the output is in G. So pretty well this is a homomorphism. Maybe we should check that. In fact, it shows some that. Alright, do I agree with it? What's that?
Excellent. That's why.
Uh-oh. Why are these two the same?
Just x y raised to p power is x p y p.
Why?
Well, it's kind of like the property of, exponentiation with multiplication.
Not in general.
No, here.
This actually, I'm glad we did this because this illustrates an important assumption in this problem. What do we know about G?
It's
It's
a deal.
abelian. This is very important. So whatever hocus pocus that I do from now on, you probably can't expect to work for a non-abelian group because the fact that this is a homomorphism is very heavily on the fact that G is an abelian group.
No, it's a abelian.
That's right.
It's rearrange the elements of x, y to p power.
That's right. Well, now that we've got this, now that this is a homomorphism, then I am going to denote let P be the kernel of theta. Right? Notice that the kernel is non-trivial, right? Because what does it mean to be in the kernel of this map? It means that the order of x is P, right? And so this subgroup of order P, this unique subgroup of order P, is killed by, I'm gonna call this. Unique subgroup of order P. Is equal to the kernel. Because basically, what that homomorphism does, the kernel of that is every element of order P or one. And that must mean it's our unique subgroup of order P. Notice also that P of G is a subgroup of G, and G mod kernel P is isomorphic to P of G, which is a subgroup. This, of course, is the first isomorphism theorem. So
That order, that's supposed to be the lowercase, right?
that's it.
There, our unique subgroup of order, that's lowercase p, right?
Yes, but there is supposed to be a capital there as well. Thank you.
Okay.
Okay, so what we have so far is phi of G is isomorphic to G mod P. And the order of G mod P is P to the n power, because the order of kernel of phi, or the order of P is exactly P. Notice P of P has a subgroup of order P. And as P of T is a subgroup of T, it must be unique. Because any subgroup order P of phi of G is a subgroup of G of order P, so there can only be one of them. By induction, P of G is simple. Because phi of G is a, group of smaller order, it's cyclic, and it's of order E to M. So, G mod P is simple. Meaning generated. Set. So the order of cosine XP is PDM in G mod P. Because it is the cyclic generator. And note that in G, the group generated by X must contain. Because this is a P group as well, so it must contain the unique subgroup order P of G. And this means the order of X in G is P plus 1, and so P. So we've made the jump up the bigger order G, and that will do it for that. So this is the first kind of big puzzle piece that we have toward classifying the finite abelian groups. Oh, by the way, I should recommend the math club. So a number of you have talked to me on and off about maybe getting involved in research. This talk will also bring up an opportunity. So it's on stuff like lattice-based cryptography, which is really hot in like doing computers and things like that and coding. I encourage you to be there if you got the time. Other than that, y'all have a good weekend, and we'll see you Monday.
This weekend.